Welcome to Study Loop.
So here we can say that one complete revolution is an angular displacement of, we can say delta theta equaling 2 pi radians. So we have 2 pi radians for every one revolution. And we can say that the angular velocity in radians per second is given by omega equaling delta theta over the period. In this case, this would be 2 pi divided by t, capital T being again the period. The angular acceleration is given by the derivative of the angular velocity with respect to time. And this would give us negative 2 pi over t squared multiplied by the change in period with respect to time. So for the pulsar described in the problem, we know that dt over dt, for the change in period with respect to time, would be equal to 1.26 times 10 to the negative fifth seconds per year divided by 3.16 times 10 to the seventh seconds in 1 year. So this is giving us 4.00 times 10 to the negative 13th. And so we can say that alpha would then be equal to negative 2 pi divided by 0.033 seconds quantity squared multiplied by 4.00 times 10 to the negative 13th. And we find that alpha is then equal to negative 2.3 times 10 to the negative ninth radians per second squared. So this would be our answer for part A. And note, the negative sign essentially indicates that the angular acceleration is opposite the angular velocity, and the pulsar is, of course, slowing down. So if we have a negative angular acceleration, the pulsar is, of course, slowing down. So we can say for part B, we can solve omega final equaling omega initial plus alpha t for a time when omega final equals 0. So t would be equal to negative omega initial over the angular acceleration. This would be equal to negative 2 pi over alpha times the period. So we can solve negative 2 pi divided by negative 2.3 times 10 to the negative ninth radians per second squared multiplied by 0.033 seconds. And we can say that t is equaling 8.3 times 10 to the 10th seconds. Or we can say approximately 26,000. My apologies, 2,600 years. So it essentially take approximately 2,600 years in order for the pulsar to come to a rest. Now, for part C, we can say that the pulsar was born 1992 minus 1054. So the pulsar was born 938 years ago. Let's calculate this in seconds. 938 years multiplied by 3.16 times 10 to the seventh seconds per year. This is giving us 2.96 times 10 to the 10th seconds. And we can figure out its angular velocity at that time. So we can say omega final equals omega initial plus alpha t plus 2 pi over t plus alpha t, rather, This would equal, rather. And so we can say that essentially omega final would be equal to 2 pi over 0.033 seconds plus negative 2.3 times 10 to the negative 9th radians per second squared, multiplied by negative 2.96 times 10 to the 10th second, so we're plugging in that time, quantity squared, and omega final would then be equal to 258 radians per second. So that would be one answer for part C. And then continuing on, we want to find the period. So we can say that t at that time would be equal to 2 pi over omega, or we can say 2 pi divided by 258 radians per second. And so the period at that time when the pulsar was born was 2.4 times 10 to the negative second seconds. This would be our second answer for part C. That is the end of the solution. Thank you for watching.